Hi everyone, and welcome to Workshop 1. My name is Tan. I'm the treasurer for the ISPOR Vic student chapter. And today we do have Petros today, who will be presenting on an introduction to cost-effectiveness analysis using R. He's based at the Hospital for Sick Children Research Institute and University of Toronto Institute of Health Policy Management and Evaluation in Canada. As you may have read his biography, Petros' research activities is in and around the use of health decision analysis in economic evaluation, bridging evidence synthesis and administrative data and decision analysis, the application and extension of predictive models in health economics, as well as other economic metric and statistical applications in health economics and health policy, such as estimation of empirical cost effectiveness thresholds. He's currently involved in a number of projects around economics of preterm birth prevention, the economic evaluation of oncology and ophthalmic interventions in children and adolescents, and the economic impact of obstructive sleep apnea and COPD in adults. So thank you, Petros, for your time today, because it is out of your normal, I guess, our usual working schedule. I'll hand it over to you. But before we do, I'd just like to have everyone ensure that their mics are on mute, and happy to receive questions as they come through the chat function. Thank you, Petros.
Thank you very much, Tan, for the introduction. And I'm glad to be with this group and having a chat about something that myself and colleagues that I closely work with, feel quite passionate about. Maybe before I start, I'd like to just, if everyone knows how to use the hand raise button, if you don't mind, so that I can tailor also how quickly we're going to go through today's lecture. How many of you have ever used R before? If you can raise your virtual hand, or yes, thumbs up, good. Cool, okay. So I'd say about half, all right. And how many of you have ever built a decision model? Okay, so about a little bit less than what, the people that have used R. Okay, so what I'm going to try to do is I'm going to give you an overview of why R is, why we think R is useful for the purpose of cost-effectiveness analysis and decision modeling. And then I'm going to try to save some time at the end to illustrate one simple model in R. We're not going to go through detail on the code because we don't have the time for it, but I want you to see essentially that it's really not that complicated. And hopefully at the end, we're going to save some time to have a little discussion about practical matters that might be of use to you. So let me start by sharing my screen. So again, I hope you can see me well, and I hope you can hear me well. If you don't, please let me know. And can you see the full screen?
Yeah, looks good, Petros. Thanks.
Awesome. All right. So often, if you have ever built a decision model, and this at least has been my experience with building a decision model from scratch back in especially before R has been so kind of prevalent in my daily life. But essentially, you would build a decision model, maybe let's say in Excel or in Triage, another software that is commonly used. And then this decision model would have its own input. And this input could come from, say, an evidence synthesis exercise, like a meta-analysis or a literature review. You could have a regression model that would be informing the model. And that could be, say, survival analysis data or patient level data, where you would do a survival analysis regression model, and that would inform transition probabilities. Then the model itself would have its own assumptions and its own input, like what discount rate or time horizon or a number of assumptions around the decision model itself. sometimes decision models need to be calibrated and need to be validated, and calibration, it has its own assumptions and input, and the all these things could be happening in separate software. For example, meta-analysis could happen, say, in Revman, and SAS is a common tool to use to build a survival analysis model. And then calibration cannot be done in Excel, so it will have to be exported into something like R. Models should calibrate it and back into Excel or 3H, and then either through that or through another software, you could, make the output look pretty and publish it. Now, this fragmented process, a challenge on this because attributable to this fragmented process is the fact that if you wanted to change something at the very beginning of your process, say, an additional patient level data set comes in, that means that you're going to have to rerun the SAS code, export that, save it in a CSV file or a TXT file, load it in Excel, rerun the assumptions there, recalibrate the model in a separate software, bring it back into Excel. And that task is laborious, and it also it's likely to generate room for errors, for like typos, for mistakes that happen by this transition from one software to the other. And I think, and also it's limiting your willingness to do sensitivity analysis or scenario analysis because it's such a laborious process. Now, one thing that R does very well is that it streamlines what you refer as decision model. And because all of these tasks that I mentioned before could be done seamlessly within one software like R, but R is not the only one, but this is an example. Like here, we're going to see an example of using a software like R to build a decision model, essentially. You can lump all your input in your components of the decision model, evidence synthesis, regression modeling, the decision model itself, into one kind of section. The process of decision modeling can be lumped into another section that would be essentially all together, and it could be nicely documented and in a logical order. And that could spit out an output that would be even publication ready, as we will see in our example. So this streamlining allows you to A, have a much faster process, B, have a way to logically logically go through the flow of all these tasks that are happening for the model to be conducted, and C, allow for multiple scenario sensitivity analysis, because this process is so it's so much easier to change something on the input and rerun the whole model. So we're not the only ones that have been advocating for that. There is a group in the UK where back in 2006 they wrote a paper about how Excel essentially is losing and should lose its place as the kind of primary software for decision modeling and in health economics. And they very nicely illustrated a number of key difficulties for building economic models in Excel. And if you have ever built or reviewed an economic model, a decision model in Excel, you must have shared the same kind of experience of having multiple seats that they need to interact with each other in a non-logical necessary order, have a VBA code in the background with Visual Basic code in the background, which would do part of the job, and then the other part of the job would be done through Excel functions. So that makes debugging very clunky and challenging, because you have to jump from one sheet to the other, and you try to understand what the process of these functions are without the formulas, without having a logical structure. The fact that you have point and click functionality in Excel makes it comfortable and convenient when you're building stuff, but at the same time makes things non-reproducible sometimes, which is a rather challenging task. You want your models to be as reproducible as possible. I mentioned the hybrid kind of structure of programs where you have to transition from SAS to Excel and from Revman to Excel and so on. And an important point is that if you want to use advanced methods, these are likely not going to be available in Excel, or they're going to be taking forever to program in Excel. I'm right now having to program something in Excel, like a microsimulation model in Excel, because it is because of the limitations of our essentially HTA agencies, or Health Technology Assessment agencies in Canada, but on what do they accept, but it's really not fun. So back in, it's a few years now, but maybe let's say 2017, I think that the work was done, no, 2016 already. We tried to calculate what is the estimated time, or what are the benefits essentially of different software and the hurdles of different software that are commonly used, and and try to kind of categorize them in a semi-transparent, in a transparent way. And one thing we learned is that R is not surprisingly quite fast. It's not as fast as MATLAB, which is another software that does that could do the same tasks, and it's much faster than a software, the commonly other used software, at least in North America, 3H, which at the time was really slow. I think by then things have improved, but essentially, if we were to summarize this paper in a nutshell, because of this source, the structure that it has, where you have a script with a logical structure, we find it to be very transparent, and you can validate the work because you can go through it line by line and understand what is done. R is fast, almost as fast as MATLAB, but maybe not as fast. R is very capable as well. It's, I think, the limit in your ability to do things in R are only, you're essentially limited by your skills only. And R is also free. It's an open source software that is free, and you can access it either for academic or commercial use. You can access it for free, which is amazing. And it also has all these packages that are on the web that they are also free. Essentially, the biggest challenge of R is its learning curve. If you've ever tried to use R for the purpose of economic modeling, you might find it that it has a steep learning curve, and R in general has a steep learning curve. But once you understand how it works, it becomes much easier. So essentially, we put together, that's what we strive for, to create materials that they can reduce or dampen this learning curve. I think that the term flattening the curve, the learning curve, is now reserved for more important things than decision modeling in R. So as I mentioned, R is an open source language, and open source and decision modeling go very well hand in hand, in my opinion, because it allows for models to become freely available, and that on its own improves knowledge sharing, improves better use of public research investments, because if you build a model and it sits on the shelf, it's not a great use to anybody. And it allows for access regardless of resource capacity, and it facilitates improvement by peer review. In open source software, you can more easily accommodate complexity, because usually the complicated routines are the complicated or cutting edge routines are usually done in an open source language, and the computational efficiency that this language offers is tremendous. As I mentioned before, the advantage and disadvantage is the fact that you are provided this freedom to create a desired modeling structure that does not really have to be set in boundaries, either because of the capacity of the software or because of a pre-specified structure that is provided to you. A great point that I would like to stress is the point of reproducibility and transparency. Putting models in the public domain is great because decisions that they're being made are based on these models, and there needs to be this kind of level of scrutiny of how are these decisions being made and why, based on what information and based on what modeling predictions. And we've seen it with COVID-19 very kind of vividly, where there was a lot of questioning on decisions, and then there was the need for some level of transparency on the modeling behind some of the decisions that were made. This allows for methodological scrutiny also from peers, which is great. I mean, at the end product, no one might like criticism for a model that doesn't work as intended, but at the end, I think it's beneficial to everyone that there is a peer review. Reproducibility is key, and it is possible to be done within
goods or services.
It's possible to be done in a series of mostly logical steps. Of course, not by providing code on the web does not necessarily make something transparent. Good coding practices and transparent structures are necessary for reproducibility and transparency. I'm not sure how, like, whether this is my personal experience with that or whether it is really true, but I think that open source modeling opens the door for collaboration much more widely than we have been used to, because putting something on the web makes it much more likely that someone is going to use it, reuse it, reach out to you for advice, and possibly collaboration. So I think it has been a tremendously collaborative space that I've worked so far. This is a paper that was published a few years back that is worth reading. I'm not going to go into detail, but this is these authors interviewed or surveyed a number of pharma, academia, and government stakeholders in health economics to understand what is their view on open source modeling. And I think that the key messages that I would like to just share is that collaboration would encourage sharing of decision models, and they stress the importance of working together, developing open platforms that maximize value of research, but confidentiality would need to be addressed in some way, because models need to be confidential when you have proprietary information. Not every HTA organization will accept open source software to when you submit, say, an economic model. And an important aspect, again, that we are also trying to focus as much as we can with our daily work is the consistent use of that open source language. Because if you think of it from the side of either the manufacturer or the HTA reviewer, you don't want to have too much heterogeneity on the types of models or the structure of the models that go in for assessment into your organization, because that would make it a very difficult thing. Again, it would increase the challenge of debugging a model or making sure that it performs as it should. Obviously, there's a downside to open source software and use of R. As I mentioned, there's a steep learning curve. Most of the people are not familiar with programming languages, and we kind of experienced it also in the beginning of the talk. There's not a lot of educational tools available. Like, there's no book on how to build decision models in R or cost effectiveness in R. That we, myself and a few colleagues, are in the process of writing 2 of those books, but they're not out yet. So the information that is available out there is relatively fragmented, but in the form of tutorials and workshops, these kind of lectures like today, but in some way there's more support than just a book, because first of all, there's an exponential growth from the information that's being generated in the field of decision modeling and R, but there's also information in the use of R that you can access freely. That is a massive help if you're building your own decision models in R. Another downside is liability. There's no liability. There's no one to blame if things go wrong if you're using an open source software like R. There are minor compatibility issues that you might experience, and that reflects for example, an updated version of R or of the software or a package that R is using that might you know, something has changed in the code in that package, and that makes your model from like 5 years ago not to run. It happens, it can happen. There are ways to avoid it, but this is something to keep in mind. Now, open access implies that you are, or using something like R would imply that if you're willing to share the code, that means you have to write your code in a way that it's ready for sharing. And that means you have to have the right annotation, commenting, structure, clarity to make sure that someone else is going to understand what you're doing. And if you're not transparent on the way you code, then this will hamper transparency of the model itself. And one last word of caution is that the fact that you have something that is powerful can also lead to creating overcomplicated models that they don't need to be as complicated just because you have the ability to do so. So we said, to recap, it's freely available, it's open source, it's flexible to implement any kind of modeling structure you can think of, it's computationally efficient, it's reproducible, and you can integrate statistical analysis with modeling like parameter estimation or the analysis or visualization of results. Back in 2005, it was the first time that I could find that someone published some cost effectiveness analysis using R, and that was by Neil Hawkins and the group of Mark Scalfer. And it was an amazing thing that they did, because it is what they did is that they published their cost effectiveness analysis, and in the appendix they threw the code. So you could go ahead and download the code, rerun the model, validate the results, modify the code, and create a model for yourself for your particular setting. So this level of transparency back in 2005 was fairly rare. So in 2015 maybe, we were teaching at the medical decision making conference, and Miriam Hunning, who is on the top right in this slide, took a course of myself, of Fernando, Haure, and Eva. Like, we were all teaching separate courses, and we were all about using essentially R in processes of decision modeling. And so she thought we need to talk, and so she put us together in a room. And since then, we have been working together, and we have developed a number of different software or different packages in R for the purpose of decision modeling. And Eline Krykam joined as a master student, and now Alan is our research coordinator. But the group that we named Decision Analysis in R for Technologies in Health, or DART for short, we try to put together papers and information materials that they would help you build your decision models in R, and we give as many workshops as we can on the side of our work. And so we say 30 workshops and 800 participants, but I think it's much more if you were to count also the 3-day workshops or 2-day workshops that we give in conferences and so on. So it has been quite, the demand has also increased over time, which is a sign of the popularity of using R in decision analysis. So the first paper we put out essentially gave an overview of R in health decision sciences. So if you're interested to learn more about what can be, what kind of software or tool projects, packages you could use in R for decision modeling, this would be a good source. We also try to scan the literature and do a semi-formal systematic review on the use of different software in decision analysis. And one thing that was quite interesting was the fact that R was the one that had an increasing trajectory over the years. It hasn't been used much back in 2000 or 2005, but it has been steadily becoming more popular in the field of decision sciences. So since then, we've published a number of papers, as I mentioned, that you can you can extract information for your own decision model if you're interested in ever using R for decision modeling. And you can download the code in all of these tutorials. The code is available and free, of course. And in particular, this need for change, it provides also a framework for building your model from scratch. So how you should set up your input, how you should set up your output, how you should set up your model itself, and also how you should structure your folders and files, and where should some structure that to get you started with it. A package came called DarfPack, which essentially has a dummy decision model that you can install on your computer and then start modifying. Because I think in reality, most of the times that's what happens. You have the structure is the same between decision models most of the times, and therefore you end up modifying an existing decision model when you're building a new one. Hardly ever you start from the scratch, from an empty sheet. Of course, we're not the only ones doing it, and that's a great thing. There's a group in the UK where we are collaborating with, led by Gianluca Baio, where they have a very similar mission. It's called R for HTA, and they also provide talks, publications, tutorials on the use of R for health economics. We are, as I mentioned before, we are writing a book together with Gianluca and Howard Thorne. So we know we are trying to work as close as possible so that we can also harmonize the type of recommendations or code that's coming out of the different groups. And you can see the link here, RHTA. They also have a workshop that's coming up, like a one-day conference on using R for cost-effectiveness analysis. So I would, if you're interested, I would suggest you visit and have a look at their activities. So also there are much more options beyond what I'm introducing to you today with respect to building a decision model in R. Some of them are more visually appealing, but maybe a bit more restrictive. Some of them rely on different methodology or different philosophy. Essentially, what I'm going to show you today is based on our philosophy that if you're going to be using a statistical software to build your model, you should be able to be in control of your model too, rather than replace Excel with an equally kind of black boxy version, or maybe Excel is not really black box, but maybe compared to 3H big black boxy version, we want whoever is going to build their model in R to be able to know what is happening. And because in R you can do it relatively easy without, you can build a model from scratch in a way without feeling that you are like I don't know who, Bill Gates or something, like you would write crazy code. And I think it is possible to be in control of your own simulation model or decision model. Two small things that recommendations that help with, if you're thinking of starting with using R for decision modeling, I would strongly recommend that you use these two tools. The one is GitHub, which became quite more prevalent by now. I think most of you or some of you might have used it already, but it's a way to keep version control for your code so that you can essentially, especially if you collaborate with others on the same code, keep track of what is changing. You don't want to have this case where something happens and all your files are gone. This is not going to be the case with GitHub, because there's a new stamp, there's a new version of your code every time you save the code. There's a new version that's being stored, and the differences with the previous save essentially is kept. so you have a record of all the changes, and this you can think of it as a web-based repository essentially for collaborating with others. And it's cheap, it's free for for private use, and it has a very friendly academia pricing if you're faculty or if you're a student at a university. It seamlessly integrates with R, and especially using through a tool called RStudio or and another tool called Markdown. So RStudio is essentially the wrapper over R. Most of you, if you've used R, you probably use it with RStudio, and that's what we're going to see today. Also, a much more attractive interface than base R. And Markdown is a markup language that can integrate essentially code, text, and graphical output in the same document. And that will allow you essentially to build your own model, write the report around your model, and publish it if you feel like, or send it for publication, or build your PhD thesis through R. And you can add bibliography, you can add like references, you can add anything you want. You can write in LaTeX. It's very versatile. So we're strongly supportive of open source software when developing decision models, as you might have guessed already from the talk so far. We suggest that you modularize your decision model, as I mentioned in the beginning, where you have input separated from the output, separated from model dynamics, or if you generate a hypothetical synthetic population, you want to generate it in a separate little section. And then you run your model, you calculate your parameter estimates, you build your regression models essentially, or your meta-analysis. You have a calibration and validation section, a cost effectiveness analysis section, and a sensitivity analysis and valuable information if that is what you're interested in. So try to modularize, because modularization allows you also to collaborate with other people more seamlessly by essentially sharing the tasks and saying, I'm going to do the inputs, you do the calibrate, the parameter estimates, and we eventually bring these two together. This is quite more easily to be done in R. One last note is you need to be consistent with your naming conventions. If you are going to be using programming, you want to be consistent with what kind of, I'm going to be always referring to P for probability, or V for vector, and N for matrix, and so on. There's a very useful tool called Shiny that allows you to build web apps from decision models, and that is great for dissemination and knowledge translation. And I'm going to show you two examples today that I think they're pretty cool. And the prettier your code looks, the better for understanding of what you have done when you go back 6 months later after your reviewers have provided input into your paper, and you're like, what the hell I was doing here? Which is exactly what, there's a paper that I have left for too long, and when I went back to it, I was like, oh, because we also evolved in the way that we think of conventions and namings and so on. Okay, so this is my short introduction to why you should be, or like how to use and why you should be using R for cost effectiveness analysis. I'm gonna try to show you a simple three-state example in R, and hopefully, I understand that. So you have a very heterogeneous level of background in R, and I'm gonna try to go as slow as time permits. But I'm going to want to make sure that we're going to end with a result. All right, so I'm going to stop sharing and I'm going to start sharing my RStudio. Any questions? I'm not sure what the structure should be, but if you have any questions, I'm okay with answering some of the questions now before we move on to the R code, if that's okay with the organizers.
Thanks, Petros. Yeah. Yeah, you can move on to the next section. I'm just monitoring the chat. One was in regard to packages that's available, sources, and I think you already provided some information about that. So that's already, the answer's already been answered. So yeah. Thank you.
And there are specific packages that they were developed for survival analysis and health economics, a package called SurveyG. And I can put them on the chat. I can just quickly these, if you were to be looking for packages in R that they do stuff for decision modeling, these would be the ones. So if you were to search for these ones, as I said, it's knowledge is fragmented at this point, but it's becoming more structured. Okay, so this is how our studio looks like. This is our studio. The essentially engine is on the bottom left, which is the R console. And on the top left, you see the code. I don't know, you can see my screen, right?
Yes, we can. Thank you.
Okay. You can see the code on the top left. This is a markdown document, which means that both language and code exist in the same place. On the right-hand side, you can see like a plot or the help files, the packages that are currently installed. R works with additional packages, as you probably know, and that's like some of the packages that I have already installed in my computer. And this code, I'm happy to share for whoever is interested, is you can use it, you can reuse it. The only thing we ask is to cite the corresponding paper so that we can keep track who uses it and how often this work is being used. And this little thing you can ignore is essentially something that controls warning messages, and you don't really need to pay attention to that. What I'm doing is I'm cleaning up my memory, and you can see that I'm writing text, and then in these gray chunks, there's the code. This is the actual code that runs, you know, that R uses to run the code. And I can go on a specific line, and then I click the run button, and this runs essentially this line, or I can click this little run current chunk and runs the whole thing. So what I do next is I load a bunch of packages that they are going to be useful as I go along with the rest of the exercise or of the building of the three-state model. So I loaded a few more packages. In fact, a package called diagram, a package called dumpack, and a package called dartools. I don't need any additional functionality. In R, you can build your own functions, and you can use them when you are, and you know, if you want to develop your models right now, everything that I need is within the dartools package. I assign variables or values, or sorry, I assign values or text to variables, so I can reuse them as I go along. And so in this hypothetical example, I need 60 cycles. My time horizon is 60 cycles, so I create a variable called n cycles and has 60, the value of 60 on it. I name the three states. You can combine like strings or values into a vector using the C function. So I create a vector of 3 elements, healthy, sick, dead, to reflect the state names, and I store it in these V name states. I assume a discounting rate of 3% for cost and qualities, and then I have 3 alternative treatments: standard of care, what happened? Standard of care, treatment A, and treatment B. Each probability, each transition, so this is a Markov model. So for each treatment, I have a probability of experiencing a different outcome, and I'm gonna essentially input it in R in this point here. So the probability of transitioning from healthy to death is 1%, for regardless of which therapy you are on. The probability of transitioning from healthy to sick is 5%. For standard of care, 4% for treatment A and 2% for treatment B. So as you can see, treatment has an effect on reducing your probability of transitioning to sick. So it spares you the sickness. If you become sick, then you have a 10% chance of dying per cycle. Okay, so these are kind of just setting the scene and loading our input parameters. We also have state rewards or cost and utility estimates. So we assume that the cost of being healthy is 400 units, dollars or euros per cycle. $1,000 if you're sick, and dying, we assume that there's no cost from dying. In additional, there's a cost of treatment for treatment A, that is $800 per cycle. If you're in a healthy state, if you become sick, you don't receive treatment anymore. And treatment B is more expensive with $1,500 per cycle. Then we assume that utility of healthy is always 1. You have a utility of 0.5 if you're sick, and you have a utility of 0 if you die. You can notice here that this hashtag and then language next to a variable is a comment, and it's there so that we can remember what every line represents. I was telling you that I like when code is pretty, and what I mean by that is, for example, here I ensure that everything is everything is aligned, so I can easily go through it and understand what's going on. Then I create variables that they are auxiliary, essentially variables that they help us understand how we can use them, reuse them later on in the code. But essentially, we create a variable that is the number of strategies, so that would be 3, and I can show you. I think if I run it, so we can, you can actually see that if you highlight it and run it, you can see that the number of strategies is 3, or the number of states is also 3, because it's essentially the length of this vector of the names of the states, healthy, sick, death, which is a vector of size 3. I also create a vector with the names of the cycles, so cycle 0, 1, 2, 3, and so on. I calculate a discount weight, which is the formula that you probably have seen in textbooks, essentially 1 plus the discount in the power of time. And I create this vector for cost and effects. So you can see that over time, we discount outcomes because they happen later in the future. Now, we have set the scene. This is the input section that I referred to before. Next thing we need to do, when you have a Markov model or a state transition model, you essentially need 2 things. You need a transition probability matrix, which you've probably seen before, which is a 3x3 case matrix in our case here that captures the transitions. And you need a Markov trace, a trace that will essentially capture state occupancy. This code I'm gonna just quickly pass because it's only there to create this figure. And this is not really relevant for the rest of this process. So what we do is we first decide where people will initiate into the model. So in that particular example, we're saying the probability of starting at healthy is 1, the probability of starting at sick is 0, and the probability of starting at dead is 0, or the proportion of the cohort, 100% of the cohort starts in the healthy state, essentially. So our initial state would be 1, 0, 0. The next step that we're doing here, and again, I'm not, in the interest of time, unfortunately, I cannot go into the details of what this code really means line by line, but I can show you what it does, is we create a trace of that is currently empty, that is going to eventually host the proportion of the cohort at different states or state occupancy. One thing we know for sure, though, is that, as we said, individuals will start in the healthy state. So this line of code, what it says is that replace the first row of that construct by 1, 0, 0. So now we have essentially said all the cohort is going to start at healthy at cycle 0. Okay, so we have initialized our cohort trace, and the cohort traces will look the same for treatment A, treatment B, and standard of care. For all these, we create cohort traces that they look identical because everyone starts in the healthy state. So our trace is ready. Next step, transition probability matrix. So we create a transition probability matrix that essentially is a 3x3 construct like that, healthy, sick, dead, healthy, sick, dead. And we slowly populate it with the probabilities that we have outlined above. So for example, we're saying the probability of transitioning from healthy to dead is equal to PHT. By doing that, you can see that our 3x3 matrix has been now death from being healthy has been replaced with 0.01. We assume that the probabilities that were provided to us are conditional on surviving. So we're saying if you have survived, then your probability of becoming sick, conditional survival, is 0.0495. So we populate the rest of the cells, essentially, of that 3x3 matrix with information that was provided to us from above. And I'm going to do that. And I'm going to show you that this really looks like a 3x3 transition probability matrix. And now, if we have our transition probability matrix for standard of care, what we can do is modify that a little bit for the treatment A and treatment B. And we know that treatment is going to reduce your probability of transitioning from healthy to sick. So that's what we update here. And it by default is going to also affect your probability of remaining healthy because you're less likely to go to the sick state. So you're more likely to stay in the healthy state. Treatment B has a similar but more pronounced effect. So we generate also these transition probability matrices for treatment B and treatment A. And you can see, for example, treatment B has a much higher probability of remaining in the health state than transitioning to sick compared to standard of care. Okay, so we build our transition probability matrix, we build our Markov trace or cohort trace like we've initialized it. Now, a Markov model really is only a matrix multiplication. Again, the tutorial is very short to be able to cover what matrix multiplication does, but if you have done matrix multiplication, essentially matrix multiplication is a multiplication and summation of all states with their corresponding probability of transitioning out of that state. Or so that if we were to illustrate it for, let's say, the first cycle, t is equal to 1, you can see that for the first cycle, individuals, as we said, start at healthy, and there's no one is sick, no one is dead. The probability, the transition probability matrix looks like that for the standard of care. So matrix multiplication, what would give you would be the proportion of the cohort in the three different states at time t+1. So by doing this simple one line of code of matrix multiplication, you can, if you have the transition probability matrix in the Markov trace, you can calculate what is the proportion that's going to be in the healthy, sick, or dead state. And essentially, we do we repeat this process for the whole duration of for all your cycles. Do that for cycle 1, 2, 3, 4, and so on. And by doing that, remember how this looked like? You remember this empty cohort trace that only thing that captures is the fact that everyone is in the healthy state. By running this like 4 lines of code, you have essentially built your model, because now you can see that people transition. This cohort trace captures the proportion of the individuals at different states as they transition over time, and you can see that it has already, like, it's running it doesn't even take a second. So if you have the cohort trace, you're almost there. You have populated your cohort trace. You can even plot it nicely if you want to see how the cohort, transitioned eventually to death. And you can see that people became sick, and then the proportion of people remaining sick has dampened because most likely people died. So you can also calculate life expectancies if that is something that you would want. Okay, we're missing one thing. here. So ignore this line. It's my fault because I removed something last minute to make it squeeze within the timeline, the 1 hour. So we can ignore that line, but the most important bit is here. You want to calculate the cost effectiveness outcome. So you have a reminder, you have this Markov trace. And what would you have done in Excel? You would have an equivalent kind of size 3 of, you would multiply this with the cost of being healthy, this with the cost of being sick, and this with the cost of being dead throughout all the cycles. And then you would sum across the 3 different states to calculate the cost of, the total cost of being in the alive, let's say, in cycle 0 or alive in cycle 1 and so on. So instead of doing these 3 steps, you can use matrix algebra again to grab this vector of 3 values, which is the cost of healthy, cost of sick, and cost of death, multiply it with the Markov trace, and what that will give you is the total cost per cycle. Okay, the first cycle, everyone's in a healthy state, so that's why the average cost is 400. Second cycle, people move to the dead state, to the sick state, which is more expensive. That's why the costs go up. Eventually, people die, and that's why costs go down as well. You can store that for the standard of care for treatment A and treatment B, and you can do the exact same thing for utilities, because utilities are also different across the different states, and use matrix algebra to calculate the total, essentially the utilities per state. Average utility, the average utility per cycle. Everyone's in the healthy state, that's why a utility of 1 at cycle 0. But as people transition to the 6th state, you see that the average utility goes down. You can discount these costs by multiplying them with this discount weight. And what you get with that is essentially the total cost per treatment discounted, which is the outcome that you're looking for. So you can essentially calculate, oops, I didn't run everything from here. And then the total costs and total utilities are your outcomes of interest, I assume. Total cost for treatment A, total cost for treatment for standard of care, total cost for treatment A. You can see that treatment A is more expensive than standard of care, and you can see that treatment B is even more expensive, discounted. You can see the utilities, the total utility discounted for standard of care, 13.6 qualis. Treatment A would yield more qualis, and treatment B would yield even more qualis. You can store them into a vector, and you can give it nice names, so it can be presentable like that. Standard of care, treatment A, treatment B, and cost and effect. But most importantly, you can use functions that are within the dump package that can help you calculate the ISRs of these strategies. And so if you provide the cost, the effect, and the name of the strategies, this function calculate ISRs will calculate the ISRs for you, and it's also going to present them in a nice table where also dominance or extended dominance is going to be, the status is going to be also identified, and accordingly present or not the ISR and the incremental cost and effects. Lastly, you can plot that into a frontier, cost effectiveness frontier, where you can also see again that the treatment A is the dominated strategy here, the weekly dominated strategy. So again, this was like a super fast walkthrough, a simple model in R. You are not expected in any way to be able to, convert to R for your purpose of decision modeling now, but I think that gives you an illustration of what you can, of how easy or difficult it is to do something like that in R. And in my opinion, it's very easy once you familiarize yourself a little bit with the code. And we don't have a lot of time, so I think I'm going to stop here. and I'm happy to take questions that you might have.
Thanks, Petros. That's a really good snapshot, and I can see how powerful it is because you can really see the lines, sort of where it references, and it sort of looks fairly similar how Stata runs in terms of you can separate the code and then put descriptors as just with the hash in front. I've got a couple of questions because I know time's just running out. Just to note that for those who are going to the meeting room for the next workshop, you need to use the ID number that's Kate has put in the chat box, and also the password as well. So please use that for the next workshop if you're going to the second workshop, breakout room 2. I've got a question from Elena, and just in regards to whether there's packages to generate outputs like a tornado plot.
Yeah, so this the package dumpack that we developed has a function in there to build tornado plots, a one-way sensitivity analysis and two-way sensitivity analysis as well. So you can do tornado plots, and you can also do two-way sensitivity analysis if you want to explore more than. So if there's a lot of functionality in dumpack to do one-way, two-way, and probabilistic sensitivity analysis.
Great. It'd be good, Petros, if you just put, because I know that you run workshops as well, so I'm sure those who want to get more familiar with using R, obviously practical experience is helpful. We'll probably just send some more information after today's session regards to the links to that
and there's
to future workshops.
I have to say that there is an upcoming workshop that is going to happen in the summer, so I can send information about it to whomever is interested, or you can feel free to email me as well with more information if someone wants. I have a pretty unique last name, so you can find me easily on the web. Yeah. Hi, Natalia.
Hi, Petros. So nice to see you.
Nice to see you too.
Good. How are you?
Good. Just finished, I think.
Yeah.
Thanks for that, Petros. Much appreciated for your time. I think we've run out of time. Our next session will start very close to 11:10. So thanks, Petros, again. And for those in the audience, feel free to have a quick break. And